Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the course Basic Organic Chemistry, CHEM-122. This is your first online lecture about alkene hydrocarbons. I am Dr.Naila Khalid, Chemistry Department, Cust, Kohart. Our present session will be about unsaturated hydrocarbons, nomenclature of alkene, structure of alkene, its stereochemistry, and preparation of alkene, various methods for the preparation of alkene. First of all, what are unsaturated hydrocarbons? Hydrocarbons are those class of compound, organic compound, which are composed of hydrogen and carbon only. Unsaturated means they have further capacity to get saturated and they have further capacity to add hydrogen. In simple words, you can say that unsaturated hydrocarbons are those which contain double or triple bond, at least one double or triple bond. So on this basis, you can categorize unsaturated hydrocarbon into two categories, alkene and alkyne. Our today's topic is about alkene. Alkene are those hydrocarbons which are composed of on at least one double bond. There may be more than one double bond. There may be two, three, or four double bond. The formula alkene, the general formula is CnH2n. You can also calculate degree of unsaturation, means how many double bonds are present, by using this formula, in ignoring heteroatoms nitrogen and halogen. Alkenes are present in nature in the form of oil of ginger. This is one of the example. In the form of protective coating of the apple. This is another example. It is also present in the form of D-limonene, which is the largest component of the oil from citrus fruit. Ethylene is used in ripening of the fruit. This is used for the ripening of the fruit. So ये जो है, it is used for the ripening of the fruit. As far as the structure of alkene is concerned, you know that alkenes are those hydrocarbons which contain at least one carbon-carbon double bond. So we will talk about the carbon-carbon double bond. If the carbon-carbon double bond is present, remember the hybridization of the carbon is sp2 hybridization. And sp2 hybridization means that there is trigonal geometry. Carbon is forming 3 sigma bonds in a plane with one unhybridized p orbital above and below the plane. So that is why this unhybridized p orbital on each carbon is now in a position to form a sidewise overlap in the form of carbon-carbon double bond. The length of the carbon-carbon double bond, this is 1.33 angstrom, length of this carbon-carbon double bond. It is shorter than carbon-carbon single bond. This shows that these two carbons are more close to each other as compared to carbon-carbon single bond. And also this is more stronger than the carbon-carbon single bond. So this is the molecular orbital picture of carbon-carbon double bond. About the ethylene, if we have any alkyl group over here, then it may be any type of alkene. This is the first member of alkene series, ethylene. Carbon-carbon double bond is very stable, is a very strong as compared to carbon-carbon single bond. It is so strong that it cannot be rotated. That is why it gives rise to two types of isomers, in which the substituents are present. If the substituents are present on carbon-carbon double bond like this, they may be either on the same side of the plane, both are on the same side of the plane, or it may be on the opposite side of the plane. So both are different from each other. This one and this one. This is cis geometry and this is trans geometry. This is only possible if you can say that you have rotated this carbon-carbon double bond and methyl gets this position and it is converted into trans. But this is not the case. This carbon-carbon double bond is not rotated at all. This is not rotated. And that is why you can say the cis isomer is a different compound than the trans isomer. And this type of isomerism, which is based on the geometry, is known as geometric isomerism. Mostly alkene hydrocarbons exhibit this type of geometric isomerism. Now we will discuss various rules for naming the alkene. The first rule is that you have to name the parent name in such a way that ending should be ene. This is 1, 2, 3. This is propene. This is ethene, cyclohexene, ENE, cyclohexene. And you have to number the longest continuous chain in such a way that double bond gets lowest position, like 1 butene, 1 pentene, 2 pentene, 2 butene, and 2 pentene. And compounds with more than two double bonds, 2 or 3 or 4 double bonds can be named in such a way that diene for 2 double bonds, triene for 3 double bonds, and tetraene for 4 double bonds. So you have to mention the position of each position of the double bond. Like here is 1, 3, 1, comma 3 butadiene. This is 1, comma 3, comma 5, 1, 3, 5 heptatriene. In the same way, this is 1, 3, 5, 7. This is 1, 3, 5, 7 cyclooctatetraene. So if you have a situation in which the alkene has a substituent as well as a double bond, you should start numbering from the side where double bond gets lowest position. So you have to prefer double bond. Here, this is 1, 2, 3, 4. This is 3-methyl butene. This is 3-methyl butene. Here it is 2-heptene, and this is 3,6-dimethyl 2-heptene. Rather than numbering from here, you have to number from here. Dear students, you can see these structures. I have numbered these structures. You have to write this in your notebook, their names, proper names for practice. If the alkene is present as a substituent, so nothing to worry. You have to write YL at the end. And if there is certain geometry, trans, cis, so you have to mention that geometry, trans in italic, and then this hash, trans, pent, 2-ene, the name of this alkene. This is cis because the two groups, methyl group and ethyl, are on the same side of the plane. So this is cis pent 2-ene. And this is the same, the substituent are opposite to each other. These two substituents are opposite to each other. Priorities are assigned if then it is more bulky. So it is trans, both are opposite to each other. This is trans. Cyclo decene. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is cyclodecene. One trans cyclodecene. Besides cis and trans form, you can also assign configuration to the double bond. If the configuration is assigned, this is EZ nomenclature, which shows that E for entity, for trans, for opposite. If the two bulky groups are opposite to each other, the trans isomer, then it is assigned as E. The geometry of the double bond, the configuration of the double bond is E. And here, the double bond has this type of arrangement. So this is assigned Z configuration. This is one of the example of Z configuration. configuration because both bulky group, methyl is bulkier than hydrogen, bromine is bulkier than chlorine. And similarly, this is 3Z because 3 is the position of the double bond and Z is its configuration. Similarly, 5E means 5 is the position of the double bond and E is its configuration, and rest of the things are same. So assigning priority, there are certain rules. Kahn and Gold pre-log system, which we have also studied in RS configuration, that is also applicable over here. Like this, methyl and chlorine. You can compare methyl and chlorine. Chlorine gets higher priority than methyl. Bromine gets higher priority than hydrogen. Similarly, this is CH2, CH2Cl, and this is CH2Cl. As this carbon and carbon are same, so you have to look for the further direct attachment. This carbon is further attached to carbon, and this carbon is further attached to chlorine, which is more bulkier. So you can say that this get higher priority than this one. Similarly, this carbon is further attached to two carbon. However, this carbon is attached to oxygen, so it gets higher priority. The rest of the things are same. Multiple bonds over here, and here is the oxygen. There is carbon. Carbon is further attached to oxygen. Here, this carbon is further attached to carbon, although 3 times, but it is attached to oxygen, so it gets higher priority than this one. Similarly, you can see also the difference over here. So, here are some structures. Draw in your notebook and try to name their structure as well as assign the E and Z configuration. Now, the stability of alkane. Alkanes are alkenes. Alkenes are stable. There are two basic parameters. Number one, their substitution, and number two, their geometry. Substitution is important. How much substituents are present, then it determines its stability. It will be more stable if it is highly substituted, and if it is less stable, if it has less substituent. So this is the criteria. And the carbon-carbon double bond, if it is present in terminal position, it is less substituted as compared to carbon-carbon double bond, which is substituted, which is in between the chain, it is more stable and is of low energy as compared to carbon-carbon double bond at terminal position with less substitution as compared to carbon-carbon internal double bond. So this is also called Sedgwick's rule. This energy diagram shows that this terminal double bond is less stable than the internal double bond. Next criteria, second criteria is the geometry, the trans isomer. This is trans 2-butene. Trans isomer is always more stable than cis isomer. Now we will discuss the synthesis of alkene. Alkenes are synthesized by various methods. This is the list of synthetic methods. You can carry out alkene synthesis by elimination reaction, thermal cracking, dehydrogenation, hydrogenation of alkyne, and Wittig reaction. One by one, elimination reaction. Elimination reaction is a reaction in which two atoms or two group of atoms, they are eliminated. And if they are eliminated, leaving behind carbon-carbon. This type of elimination reaction is known as removal of hydrogen and bromine. This is dehydrobromination. In the presence of base, it will be eliminated to give you propene, and these are the side products. Any type of base you can use for this type of elimination. This is known as dehydrobromination. Dehydrobromination, removal of bromine and hydrogen at the same time. Any type of base you can use: tertiary butoxide, diisopropylamine, triethylamine, and 2,6-dimethylpyridine. So if the base is bulky, then it will avoid any type of side reaction like diisopropylamine. This is very selective and it will eliminate bromine and hydrogen in a very efficient way. Give you cyclohexene 93% yield. You can also carry out elimination reaction of vicinal dibromide. This is vicinal dibromide. In the presence of iodide, in acetone is acting as a solvent, and you just go for the elimination. This is not the dehydrobromination, this is debromination, or in generally dehalogenation. This halide will attack over here. This double bond is shifted in this bond is shifted and to form a double bond, and this bromide is also leaving this molecule. Third type of elimination reaction, you can carry out elimination reaction with alcohol. So this is about your starting material. If your starting material is alcohol, this OH, you know that this OH is not a good living group. So you have to put acid. Acid will protonate it and it will leave the surface and leaving behind carbon-carbon double bond. Here is its mechanism. Focus on it. This OH will get proton and then protonated by sulfuric acid. This is the structure formula of sulfuric acid, and then this OH2 get eliminated in the form of H2O. Water is eliminated and leaving behind carbon-carbon double bond. Now, second method of synthesis of alkene is you go for thermal cracking. If you have alkene, you heat it in the presence of catalyst, it is cracked into lower alkane as well as some of the alkene. Third method, dehydrogenation of alkane. So you can carry out dehydrogenation, catalytic dehydrogenation of alkane, and it will remove two hydrogen, but it is very at high temperature and at high pressure and high temperature. In the presence of catalyst, it is dehydrogenated. Removal of hydrogen from here, and from here give you carbon-carbon double bond. Fourth method is about the hydrogenation of alkyne. You can carry out hydrogenation of alkyne in a controlled manner. This is alkyne 1, 2, 3, 4. This is 2-butene. This 2-butene get hydrogenated to give you cis-butene, cis-2-butene. It is further hydrogenated if it is not controlled. Lindlar catalyst is used in this case because it will poison the catalyst. We stop the reaction at this stage where this carbon-carbon double bond is not further hydrogenated in the condition if you have used some poison like Lindlar catalyst is used. Last method of synthesis of alkene is Wittig reaction. This Wittig reaction is designed by Wittig. This is carbonyl compound, carbon oxygen double bond. This carbonyl compound react with this Wittig reagent to give you this type of highly substituted alkene in a very efficient way. This is the triphenyl phosphine oxide, its byproduct. At the bottom, you can see the mechanism of this reaction. This is acting as a carbonyl, carbon with negative charge. This is acting as a carbonyl. This is actually Wittig reagent. This will attack over here, and this comes here, and cyclization take place. And after cyclization, this is converted into triphenyl phosphine oxide like this. This double bond, this will move here, this will move here. A carbon-carbon double bond is formed in this way. Now the summary of this session, we have discussed about the nature of the double bond and its geometry, IUPAC nomenclature of alkene hydrocarbons, and some of the preparation methods of alkene. That's